welcome back. So, this lecture is about cause-effect relationship. In the last lecture, we discussed about strain, and the lecture previously we discussed about stress. Now, in this lecture, we will be combining these two. So, that is known as cause-effect relationship. Okay. So, solution to geomechanical problems, it should satisfy, the first one is stress equilibrium, which is considered as a cause. Now, as I discussed before, stress is not actually the cause is the external loading, but the internal mechanism is understood as stress. So, do not get confused with that stress is a response. So, how it can become a cause, but this is due to the external load which is acting. The manifestation of external load is conceived as stress. So, stress is the cause, that is how it is taken, and the effect would be strain. So, we need to satisfy stress equilibrium condition, which is conceived as the cause. Then we also need to understand the strain displacement relationship, which is defined as the effect, and to ensure compatibility. Then it is cause effect relationship, and in most of the cases, for simplicity, it is assumed linear for elastic behavior. Now, why I have specified it here is to make you understand cause effect relationship really talks about the material behavior. Now, cause effect relationship, why do you need that such a relationship, that also will become clear subsequently. We need to study about stress, we need to study about the strain, why you need to connect these two. So, that it will be clear in some time. So, it is assumed for linear for elastic behavior. Now, it is all about our understanding about a given material. We know that soil and rocks, they behave non-linearly, but there are certain situations and conditions where soil can also exhibit linear behavior. So, if you assume the cause effect relationship essentially depends upon what kind of response the material give for a given set of loading, and depending upon the constitutive behavior of that particular material. Now, step C, that is what it means. The step C involves material constitutive behavior, how whether a material should respond linearly is mostly dictated by the material itself. A very good example would be of that of over consolidated soil. It is the same soil, but it has undergone a lot of stress in the past. So, the present stress what it is subjected to is in fact very small for that material, and in those conditions it can exhibit a sort of linear behavior. So, what type of response a material should exhibit will depend upon the constitutive nature of that particular material. And then we need to also satisfy the boundary condition, both in terms of force and displacement. So, these are some of the minimal requirements to solve problem in geomechanics. So, in that we have discussed about stress, we have discussed about strain displacement relationship. So, in this lecture we will specifically understand the cause effect relationship. So, to summarize, this is about the stress equilibrium equation, which we have already discussed before. Just for completeness, I am again repeating it. Again, the strain displacement relationship, which is the effect, linear strains epsilon x, y and epsilon z, and shear strain, which is the engineering shear strain, is given in this manner. I will not spend time here, we have already discussed this. Now, considering stress equilibrium and strain displacement relationship, there are 6 stresses, independent stresses, 6 strains and 3 displacements. Altogether there are 15 unknown quantities. Now, 3 equations of stress equilibrium, 6 strain displacement equations amounts to 9 equations. Again, number of equations are way less than the unknown quantities. So, for solving the problem we need 6 more equations, and this comes from the constitutive behavior or constitutive relationship. Why we need to connect stress and strain or cause and effect, because that process will give you additional 6 equations with which one can solve the given geomechanical problem. The constitutive relationship is extremely important for any material, and we need to spend a lot of time learning if you want to master geomechanics. This is the constitutive relationship is extremely important. So, constitutive relationship represent how a material respond to external stresses. For a given problem, rather a given linear problem, this is the cause, this is the effect, and this is the constitutive behavior or the constitutive relationship is ensured through this particular matrix. For here it is given as 6 by 6, we will come to this a bit later. And for materials like soils which are highly non-linear, it is always ideal to talk in terms of incremental stresses and incremental strain. So, this is what is denoted here, delta sigma and delta epsilon. The other thing remains the same, the constitutive matrix that remains the same. So, cause effect relationship. Now, it is always easy to start with most simple part of the constitutive relationship or cause effect relationship. That is why we want to discuss the for perfectly linear elastic material with the exemption of homogeneous and isotropic. I hope all these terms are known to you. Homogeneous means spatially it is all same, and isotropic it is same in all directions, and it is a linear elastic material. There is a very fundamental relationship between stress and strain, where epsilon x, which is the linear strain in x direction, you can write in terms of stresses as sigma x by E minus mu by E into sigma y plus sigma z, where sigma x is the normal stress in x direction, E is the modulus of elasticity, mu is Poisson's ratio. Similarly, you have, that is what is written here, Young's modulus, Poisson's ratio. There is one more term called G, which is the shear modulus. So, similarly, you have epsilon y and epsilon z. In addition, one can always write the shear strain gamma xy is equal to tau xy by G. Accordingly, gamma yz is equal to tau yz by G, and gamma zx is equal to tau zx by G. So, these are the set of constitutive relationships if you consider a body to be linear, elastic, homogeneous and isotropic, where G is the shear modulus and it takes the relationship E divided by 2 into 1 plus mu. One important thing we have to note here is in all these expression E and mu, they are the only 2 parameters which need to be known to define the constitutive behavior. G is a dependent parameter and it depends on the value of E and mu. So, we have 2 independent parameters we should know. Now, when you take into account the cause effect relationship, we are left with now 15 unknowns and 15 equations, and the problem can be solved. So, the cause effect relationship, it is written in matrix form, where E epsilon is the strain, E is the constitutive matrix and sigma is the stress matrix. E represents the material characteristics, and here again we will be dealing with homogeneous, isotropic, linear elastic behavior. This reduces E matrix to comprise of only 2 unknown parameters which related to material behavior, which is E and mu, and which can be determined using suitable laboratory tests. So, that is how it looks like: epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx, the corresponding stresses, and 6 by 6 matrix of material behavior. And for linear elastic material, one can always obtain, and this formulation of matrix comes from the previous slide. We have the relationship, so that is rearranged in matrix form, that is all. So, this is a simple relationship wherein we talk about the linear elastic behavior, and that is why this particular model is so popular. So, if one can define the behavior of the material using linear elastic, then it considerably simplify the problem and it becomes less computationally intensive. So, volumetric strain under stresses is sigma x, sigma y, sigma z, this we have already seen, and if you expand, you can write as 1 minus 2 mu by E sigma x plus sigma y plus sigma z. So, expression for bulk modulus, now there are two more parameters. Sometimes it is expressed in terms of K and G, in some cases it is represented in terms of E and mu. Whatever be, all these terminologies, parameters should be familiar. So, expression for bulk modulus corresponding to hydrostatic stress condition is just to understand the expression for K, which we already know, but just to have a discussion in terms of, let us say, whatever we have learned till now. Now, what is meant by hydrostatic stress condition? Stresses are equal in all direction, that means sigma x equal to sigma y equal to sigma z. So, bulk modulus, how do you define? It is volumetric stress upon volumetric strain, and this is the condition for hydrostatic condition. This is the expression sigma x equal to sigma y equal to sigma z equal to volumetric stress sigma v. If you substitute this back into this equation, which is the expression for volumetric strain, you can get the expression sigma v by epsilon v, which is nothing but the bulk modulus, is equal to E upon 3 into 1 minus 2 mu. So, K is nothing but E divided by 3 into 1 minus 2 mu, and you can see that both K and G are dependent on E and mu. So, it is not independent. So, now we have E is equal to 3K into 1 minus 2 mu. E and K are positive because they are material constants, which means to say 1 minus 2 mu should be greater than 0 because E has to be positive. For fulfilling that condition, we can write that Poisson's ratio is always less than half. Now, in general, Poisson's ratio varies between 0 and 0.5. Now, there are certain materials which assumes the value of Poisson's ratio close to 0. For example, cork is a classical example, and in general, for most of the problems in continuum mechanics related to soils and rocks, the variation we will consider around 0.1 to 0.5. We do not talk about mu close to 0, and you will be surprised to see there are certain materials where mu is even negative. These are called auxetic materials. You can refer to literature, and basically these are engineered materials mostly, and which exhibit negative Poisson's ratio, but that is not relevant for this particular course. Now, for mu equal to 0.5, in the previous relationship, if you substitute mu is equal to 0.5, that is Poisson's ratio equal to 0.5, then the volumetric constant or bulk modulus, it tends to infinity, which implies that the volumetric strain is equal to 0. There is no volumetric strain, the material is incompressible, body undergoes no volume change, it is basically incompressible. This definition has got some meaning in soil mechanics as well. So, undrained condition, we will be discussing about drained, undrained condition in detail, but since this is a undergraduate portion, all of you will be knowing what is meant by an undrained condition, loading under undrained condition. So, what happens during undrained condition? You are not allowing the water to move out of the soil during loading. So, in that case, it is a typical case of no volume change. When there is no expulsion of water, then you cannot have volume change. What will happen? Pore water pressure will increase. So, there is no volume change, the whole of the soil mass behaves incompressible. So, what does it mean? It means that for undrained condition, one can take the value of Poisson's ratio equal to 0.5. So, the whole discussion is basically for that. So, in geomechanics we actually refer to the mu value from 0.1, 0.2 to 0.5. For purely undrained case for soils, undrained loading, one can always presume mu is equal to 0.5. To summarize the whatever we have just told about cause effect relationship, we have solution to geomechanical problem involves stress equilibrium equations, strain displacement and cause effect relationship. So, 15 unknowns, 15 equations. Considering above, there are 15 unknowns and 15 equations for solution. Cause effect relationship for linear elastic homogeneous isotropic material has been discussed in this particular lecture. There are only two material constants for the above case, and that is the simplicity of this model where we discuss in terms of E and mu. And Poisson's ratio mu is equal to 0.5 for undrained incompressible condition. So, that is all for this lecture on cause effect relationship. We will briefly discuss about some classical constitutive relationship which you normally see in geomechanics. Again, it will be a very elementary discussion which we will see in the next lecture. Thank you for now.